Angular momentum. In the previous chapter, we learned that linear momentum was mass in motion in a linear direction, in which P stood for linear momentum, m was the mass or the inertia of the object, velocity v. Angular momentum is mass in rotational motion. The symbol for angular momentum is a capital L. Its resistance to motion is I, which is the moment of inertia or rotational inertia, and omega is the angular velocity that makes the object rotate. You also know that the moment of inertia will change depending on how the mass is distributed. For the AP test, you should memorize that mr squared is for or point particles. Both linear and angular momentum vectors. The units for linear momentum, remember, mass was in kilogram, SI, velocity is meters per second. For angular momentum, I, which in generic is k, which is a constant depending on the object, times the mass, r squared. Mass SI units is kilogram, r is the distance, so it's going to be meters squared. Omega is angular velocity, which is in radians per second, or kilograms meters squared over seconds. For angular momentum, there are two generic equations that you need to memorize. For angular momentum, there are two generic formulas you need to memorize. If it is a point object that is accelerating around a fixed point, angular momentum is equal to r, the distance from the radius, times momentum. And we know that momentum is mass times velocity, so you should memorize that for point objects, angular momentum is rmv. The distance r from the axis of rotation, mass of the object, and the velocity that it is moving. For extended objects, so extended objects are objects with multiple parts rotating around a fixed point. Angular momentum will equal to I, which is moment of inertia, times angular velocity. And as we stated, depending on the object, I will vary. So we also learned that momentum can be conserved. In linear momentum, P initial equals P final if there is no external force. And we derived the momentum equation from Newton's second law. This is also true for angular momentum. Angular momentum initial will equal angular momentum final if there is no external torque. Just as we calculated for linear momentum, we only worried about what happens right before the collision and right after the collision. We don't calculate for what happens during the collision. This is a problem we did in class. Pause the video, redo your problem, and check your answer. So here we have a projectile traveling at a constant velocity towards a stationary disk. It strikes the bottom of the disk, which is down here. What is the final angular velocity? Momentum is conserved because there is no external torque. So we could write that L initial is equal to L final. There are two possible angular momentum at the beginning and two possible angular momentum at the end. we have the angular momentum of the particle or the projectile plus the angular momentum of the disk, and this can be true for at the end. And I labeled the final primes to say they are not the same. Initially, the disk cancels out. Why? It is at rest. So all we have is the angular momentum of the particle. Since this is a point object, the angular momentum becomes mass times velocity times r, which is the distance from the rotating axis. It is always the closest distance, the shortest distance from the rotating axis. So here will be right before it hits, and this is my distance, which is just the radius of the disk. At the end, we know that the disk and the projectile are together and they're moving together. So if they are moving together, they're going to have the same angular velocity. So this is going to be I of the projectile plus I of the disk times omega. Remember, generic formula for angular momentum is I, which is moment of inertia, times angular velocity. For the particle, we know that moment of inertia is mr squared. This is the particle. For the disk, it is 1/2 mr squared. If I plug this in, this will be mr squared of the particle plus 1/2 mr squared of the disk. And since they have the same angular velocity, omega, we know that Vr is of the particle at the beginning. So if I plug this in, this is 0.20 kilograms. The velocity given is 2. The shortest distance was the radius, which is 0.1 meter. This is equal to the mass of the projectile times the radius, which is 0.1 meters squared, plus 1/2 mass of the disk, which is 2.50 kilograms, times the radius of the disk, which is 0.1 meters squared. This whole thing is going to be multiplied by omega, and we're looking for omega. We could do some simplification if you want here. We know that 0.1 will cancel out with a 0.1 here and a 0.1 here. Now do your calculations. Omega equals to 2.758 rads per second. To find the energy loss, we need to find the initial energy, the final energy, and the change in energy, because what energy loss is going to be KE over KE initial. The KE initial is only from the particle because the disk is at rest. So KE initial is going to be 1/2 mass times velocity squared, and it is a translational motion because it is not rotating. So this is 1/2 0.20 kilograms. Velocity is 2.00 meters per second. You're going to square that, which equals 0.4 joules. My KE final will have rotational, so it's going to be 1/2 I omega squared, which is equal to 1/2. Remember, I is going to be I of the particle plus I of the disk because they are together, omega squared. This is 1/2 mr square of the particle plus 1/2 mr squared of the disk. And this entire thing is going to be multiplied by omega squared. So if I plug this in, this is going to be 1/2. The disk is 0.2 kilograms. R is the radius again, which is 0.1 meters squared plus 1/2. The disk is 2.5 kilograms times 0.1 meters, which you could pretty much pull out because it is the same, multiplied by the omega, which we calculated as 2.76 rads per second, and we're going to square that, which equals 0.0552 joules. So I need to do change in kinetic energy, which is KE final minus KE initial divided by KE initial. So this is going to be 0.0552 joules minus my initial, which is 0.4 joules divided by 0.4 joules, which will equal to 0.861 fraction. This comes out negative, so this means it was lost. If I multiply it by 100, it will be 86.1%. So in this problem, we have a particle mass that is 0.4 kilogram attached to a meter stick at one end and is being rotated. We are calculating the angular momentum at the pivot point when it is at the 50 centimeter mark and 0. So if I draw this meter stick as a top view, the bottom I'm going to label as 0 centimeter. The mass is attached at the 100 centimeters, and that means we know that it's being pivoted during the 50 centimeters. So L is equal to I omega. We know what omega is, so I need to find I, which is the rotational inertia. So rotational inertia is going to depend on the inertia of the particle plus the inertia of the ruler or the stick. The general formula, since it is pivoting about somewhere around the center, the rotational inertia for the meter stick is 1/12 mL squared. This is going to be multiplied by omega. We know for point masses, it is mr squared plus the moment of inertia of the stick, which is 1/12 mL squared. And this whole thing needs to be multiplied by omega. Plugging numbers in, the point mass is 0.400 kilograms. The radius is from the pivot point, which is at 50, so this is my R. So it's going to be 100 centimeters minus 50 centimeters. We need to convert that into meters. And then after that, we have to square it. Plus 1/12. The mass of the meter stick is 0.100 kilogram. The length of the meter stick is 100 centimeters. That needs to be converted. So that's 100 centimeters. 1 meter. It has to be squared. The entire thing needs to be multiplied by omega, which is 4 rads per second. This equals 0.433 kilograms meters squared over second squared. At 0 centimeters, that's where the pivot of axis is. This one you could drop. This is a parallel axle theorem. So what's happening here, if you decide to do it, is the pivot point is at 0. And we do this because the pivot point keeps on changing. So when we do that, the center of mass is located, so we must include that as part of our angular momentum. So when I write my equation, I is still I omega. We still have moment of inertia due to the particle plus the moment of inertia due to the stick. But now we must include the moment of inertia of the center of mass because the center of mass is no longer at the axis of rotation times angular velocity. Since it is the same stick that we've been using, this is the parallel axle theorem. The equations are all the same except for we add the center of mass. So that's going to be mr squared of the particle plus 1/2 or 1/12 ml squared of the stick plus mr squared of the center of mass. And after you plug all these in, you're going to multiply by omega, which is 4. So if I plug my numbers in, this becomes 0.4 kilograms. Now, since this is my rotational, my particle is still outside. So now this becomes 1 centimeter or 100 centimeter. Need to convert it, so that's 100 centimeters to 1 meter. And you need to square it because this is the distance from the axis of rotation to the particle plus 1/12. The mass of the meter stick is still the same, so it's 0.100 kilogram. And the length is still the same, so it's going to be 100 centimeters. 1 meter is 100 centimeters squared plus the mass of the meter stick, which is still 0.100 kilogram, but my center of mass from my pivot point is only 50 because it's halfway. So this is going to be 50 centimeters, 100 centimeters, 1 meter needs to be converted, squared, and then the entire thing is going to be multiplied by 4 rads per second. If you do the math, you should get around 1.73 kilograms meters squared over second. You will not see parallel axle problem on your test. In this problem, you have a uniform rod, mass 100 grams, length 50 centimeters, rotates in a horizontal plane about a fixed vertical and frictionless pin through the center. So if I draw my picture, I already know that this is my axis. We have 2 small beads that are 30 grams that are mounted on the slide that are able to move back and forth, and they're mounted 10. So we have one right here, we have one right here, and so this is 10 centimeters, and this is 10 centimeters from the axis. Find when the beads reach the end of the rod. So this is a conservation of angular momentum because it's frictionless, so there's no external torque. So this is L naught is equal to L final. The initial L's, there are 3. We have the L of the bead, we have the L of the bead plus the L of the rod. At the end, we will have the same thing. We'll have 2 LB plus L of the rod. We know the L beads are all the same, so we could even combine them. Since these are point masses, this is just going to become 2 mr squared. This is the bead. So for point, we know these are mr squared. And since this is a rod rotating at the center, we know that the rod is going to be 1/12 ml squared. So for the rod, I'm going to write in 1/12 ml squared. And the entire thing has to be multiplied by the initial angular velocity. At the end, we know that the beads are going to the same distance, so they are going to be added together again. This is B and plus the rod, and this will stay the same. The entire thing is going to be multiplied by angular velocity final. So we have 2. The mass of the beads are 30 grams. That needs to be converted into kilograms. 1,000 grams and 1 kilogram. This is going to be multiplied by their distance from the axis, which is 10 centimeters. Need to be converted into meters. This has to be squared plus 1/12. The mass of the rod is 100 grams. Need to be converted. The distance of the rod is 50 centimeters, which needs to be converted. This is squared. The entire thing has to be multiplied by the initial velocity of 20 rads per second. This is equal to, again, 2. The mass is the same. The radius is going to change because now the objects are on the outside. So outside is going to be, this entire thing is 50, so it's going to be half of that, so it's 25 centimeters. Convert it. It has to be squared plus 1/12. And the rod did not change, so we just copy what we had on the other side. The length is still 50. This is 1 meter, 100 centimeters squared. The entire thing is going to be multiplied by omega final, which is what we're looking for. If you notice in this problem, there was a lot of parts that you did not have to convert because it cancels out. If you notice, you have 1/kilogram in each of the factors. You also didn't have to convert to centimeters because they all canceled out. And then all you had to do was multiply. So omega equals to 9.20 radians per second. So they want the speed when the beads fly off. When the beads fly off the stick, it becomes tangential. Because why? It's circular motion at that instant. It becomes tangential, or velocity, which is just linear velocity. So V tangential is radius times omega. And since the entire thing is moving at the same speed of 9.2 rads per second, because they cover the same angular position each time, and then the radius is 25, this one we must convert to get proper units. So this is 100 centimeters to 1 meters times omega, which is 9.20 rads per second, equals 2.3 meters per second. So here we had to convert. Here you can convert, but if you notice, everything cancels out. Right here. So the last question is, what is the angular speed of the rod? Since before the beads leave, they are all moving at the same unit. So that means they're covering the same theta each time at a given unit of time. So the rod is also moving at 9.2 radians per second. Summary. Remember, point masses, angular momentum is linear momentum times radius. Linear momentum is mass times velocity. And when we are talking about radius here, it is the shortest distance to the pivot point. If it's an extended mass, meaning an irregular object where different parts of the mass all rotate together, the general formula is moment of inertia times angular velocity. Remember, the moment of inertia changes depending on what the shape of the object is. You need to memorize mr squared. Everything else will be provided for you. Conservation of angular momentum is very similar to conservation of linear momentum. This applies when objects are rotating. Conservation of angular momentum states that the initial angular momentum is equal to the final angular momentum as long as there's no external torque. So that means there's no friction, outside torques that are being applied. The easiest way to do angular momentum is draw a picture. Once you draw the picture, locate the pivot point. Once you locate the pivot point, you need to determine which formula for moment of inertia you need to use. Each object that is rotating must have its own moment of inertia equation. The only thing that will not rotate initially or after is if it's a point mass that is traveling linearly. And when that happens, the angular momentum will be mvr. However, if it is rotating this point mass, the moment of inertia will be mr squared. When we have objects that are rotating together, they will have the same angular velocity because they will cover the same angular position at the same given time. So these 4 things will help you solve, but it's best that you draw a picture, locate your pivot point, and write an equation for each of your object.